This video is going to cover Section 2.1 regarding complex numbers, and the learning target is that you should be able to add, subtract, multiply, divide, and simplify complex numbers. So to begin with is just a little comic strip that you might have seen before, and it's I saying to pi to be rational, and it's pi telling I to get real. The reason it's telling it to get real is because I is what we call the imaginary unit. So now what I want you to think about is if I were to ask you to solve this equation, x squared plus 16 equals 0, you are solving for the x-intercepts of this parabola. Well, the first step would be to subtract 16 from both sides, and then the second step would be to take the square root. Well, you've learned up until now that you can't take the square root of a negative number, that it doesn't exist. But there have been mathematicians that decided to give this a name, a negative square root, and that's called the imaginary unit. So I could simplify this to be the square root of 16 times the square root of negative 1. Square root of 16 is 4, and then mathematicians decided to call the square root of negative 1 the letter I, standing for the imaginary unit. And so I represents the square root of negative 1. And so now what we're saying is that you can take the square root of a negative number, and it's just going to be an imaginary number. And we're saying that all parabolas have roots, so we're not going to call them x-intercepts anymore, but all parabolas have two roots. They might hit the x-axis twice, it might hit the x-axis once, or it might not hit the x-axis at all, meaning it's going to have two imaginary x-intercepts. Imaginary unit is used for complex numbers. So a complex number is of the form a plus or minus bi. This is what we call standard form, and the a is represented by the real part, and the bi is the imaginary part. So now every number that you know can be written in complex number format. So the number 5 is also a complex number. It just has an imaginary part of 0. Or you could have 2i, which is a complex number, and it has a real part of 0. So all numbers that you know can be written in the complex number or standard form of a complex number. So first, in adding and subtracting complex numbers, it's very similar to combining like terms. So you add and subtract the real parts, and then you add and subtract the imaginary parts. So what I said, it's just like combining like terms. So you can kind of treat the I as if it were an X. So the first example that we have is 5 minus 11i plus 7 plus 4i. And so in adding and subtracting, you just add the real parts together. So I have a real part of 5 and a real part of 7, which is going to make 12. And then I have an imaginary part of negative 11 and 4i, and when I add those together, I get negative 7i. So I have 12 minus 7i. The second example I have is negative 5 minus I, and then minus a negative 11 minus 6i. Now, don't forget when you're subtracting this, you have to distribute that negative. And so the negative 11 will become a positive, and the negative 6i will become a positive 6i. So then I have negative 5 plus 11, which is going to be 6, and negative I plus 6i, which is going to be 5i. So it's just like combining like terms. You only add the numbers together that don't have an I, and then you add or subtract the numbers that do have an I together. In multiplying complex numbers, you do the same thing that you do as if it were an X. You can distribute, you can FOIL, or use the box method, whichever you prefer. And then when you're all done, just don't forget to simplify your final result, simplify the product. So our first example we have is 4i times 3 minus 5i. So I'm going to distribute the 4i once my screen comes down here. So when I distribute that, 4i times 3 would be 12i, and then 4i times a negative 5i would give me negative 20i squared. Now something I want you to think about is if I is represented by the square root of negative 1, then that must mean that I squared is the square root of -1 times the square root of -1, which just simplifies to -1. So anytime you have I squared in a product, I want you to simplify it down to -1. So then my product would be 12I minus 20 times -1, and then that simplifies to 12I plus 20. And so this is in standard form too, it's just that the BI is before the A, and that's okay. The next example I have are two binomials of imaginary or complex numbers. So I have 7 minus 3I times a -2 minus 5I. And so what you want to do here is, whichever you prefer, either the FOIL method or using the box method, is to multiply these out. I'm going to just do FOIL. And when I do that, I get 7 times -2 is -14. Then I get 7 times -5I is -35I. -3I times -2 is a positive 6I. And then -3I times a -5I is 15I squared. Now this isn't simplified, it's not in standard form yet, so I'm going to combine like terms. My -35I and 6I is going to equal a -29I. And then don't forget, I squared is the same thing as -1. So -14 minus 15 would give me -29. So my final answer is -29 minus 29I. And that's written in standard form, and my answer is simplified as much as possible. Before we get into division, we need to talk about something called complex conjugates. A complex conjugate is an opposite. So if you think of A plus BI as a complex number, its complex conjugate would be A minus BI. And when complex conjugates are multiplied together, they just simply multiply to A squared plus B squared, which is a real number. And I had to introduce complex conjugates because we are going to use these when it comes to division. So first, let's just practice finding a complex conjugate and then multiplying them together. So what is the complex conjugate of 3 minus 4I? Well, just take the opposite in the middle, and so then you'd get 3 plus 4I. And then multiplying these two together, if I were to box or FOIL it out, I would get 9 plus 12I minus 12I minus 16I squared. And so you can save yourself the time and not multiply those middle terms, because these will just cancel out. So then I'd be left with 9 minus 16I squared, which, remember, I squared is the same thing as -1. And then once I simplify, that becomes 9 plus 16, which is positive 25. So I just multiplied two complex numbers together. They were complex conjugates, and the product is just a real number, number 25. So with division, what you need to do is, when it's going to be written in the fraction format, is that you have to multiply the top and bottom by the conjugate of the denominator and then simplify it to standard form. Now the example I have in this video is different than the one that is written on your page, so if you could please cross out your numerator of 2I and rewrite it as -5 minus I. So I changed the example that's on your page. So in dividing complex numbers, I need to multiply the top and the bottom by the conjugate of the denominator, and the denominator, remember, is the bottom. So I'm going to multiply the conjugate, or multiply by 1 minus I. And so then I'm going to do box method or FOIL on top. I'm also going to do box or FOIL on the bottom. So I FOIL. And so when I do that, I get -5 plus 5I minus I plus I squared on top. On the bottom, I get 1 minus I plus I minus I squared. And then just simplifying it from here, my numerator is going to simplify to -6 plus 4I. And the bottom is going to simplify to 1 minus a -1. And then that simplifies to -6 plus 4I over 2. And then each part can be divided by that 2, and I'm left with -3 plus 2I. So dividing these two complex numbers, remember to multiply the top and bottom by the complex conjugate of the denominator, the bottom part. The pattern of I. So there is a pattern with every fourth value of I, so every fourth power. So I'm going to show you this table that I'd like you to fill in on your page. So anytime you're simplifying complex numbers or a problem, I want you to use this table. So I, we're just going to write as I. Remember, I squared simplifies to -1. I cubed is the same thing as I times I squared. So I cubed would be I times -1, which is just -I. I to the fourth is the same thing as I squared times I squared. -1 times -1 is just a +1. And then you'll see that I put a little red dashed line here because then I to the 5th is going to just simplify to I to the 6th simplifies to -1, I to the 7th negative I, and I to the 8th 1. And so it repeats every 4th power of I. So to simplify any power of I, what you need to do is divide the exponent by 4, and the remainder tells you which power of I to simplify to. So I'm going to close my screen here. Let's start with the first example. If I asked you to simplify I to the 144th power, to simplify it, divide the exponent by 4. 144 divided by 4 equals 36, with no remainder left over. 4 goes into 144 evenly. And so since there is no remainder, that means that I to the 144th is the same thing as I to the 4th power, which equals 1. My second example is I to the 49th power. 49 divided by 4 is just going to be 12, because 12 times 4 is 48, and then I have a remainder of 1. So this is telling me that I to the 49th is going to be the same thing as I to the 1st power. That's what the remainder comes in, which is just the same thing as I. So I wouldn't have to write it as I to the 49th. I could just say that that's I. My third example is I to the 391st power. If I divide 391 by 4, I get 97 with a remainder of 3, and so this is telling me that I to the 391st power is going to be the same thing as I to the 3rd power, which is the same thing as -I, looking at my table. Try the last one on your own, I to the 22nd, and see if you get the answer that I'm going to show in just a minute. So divide 22 by 4, you're going to have a remainder of 2, which is the same as I squared. And so then I to the 22nd just simplifies to a -1. Roots of negative numbers. I want to tell you that 4i and -4i are both roots of x squared equals -16, because when you take the square root you always need that plus and minus. But 4i, the positive, is called the principal square root, and this root is used when you're simplifying expressions. So the first example I have here is the square root of -25 times the square root of -4. First of all, you can't just multiply these two together. Products of radicals only applies to real numbers, so you can't multiply these together like we can if these had both been positive. So when I simplify the square root of -25, I'm going to just get a positive 5i. The square root of -4 is just a positive 2i. I'm using the principal root, because you'll notice these are all, the square root is already given to me and they're both positive. If this had been a negative out in front, then I would have used -5i. When I multiply these together, I get 10i squared, and 10i squared simplifies to -10. The second example I have is the negative square root of the square root of -27 plus the square root of -48. I'm going to simplify these down. The square root of -27 can be rewritten as the square root of -9 times the square root of 3. Square root of -48 can be rewritten as the square root of -16 plus times the square root of 3. And notice that I made the perfect square the one with the negative. So I didn't have this be the square root of -3 with a positive 9. I made it with the perfect square. So then when I take the square root of these, the square root of -9 is just 3i, square root of -16 is 4i. Leave the square root of 3 as is, and then I can simplify this one step further to get 7i times the square root of 3. The last example I have is -2 plus the square root of -3 squared. Now remember, squaring a binomial, you can't just apply the square to both parts. This means to multiply it by itself. So I'm going to write this out all together. Do the box or the FOIL method, whichever you prefer. When I do FOIL, I get 4 minus 2 times the square root of -3 minus 2 times the square root of -3 minus 3. The square root of -3 and the square root of -3 just simplifies to -3. Combine like terms, and I'm going to get 4 minus 3 was 1, and then I have -2 and a -2 square root of -3, which is just going to be -4. And then you'll notice my square root of -3 became a positive square root of 3, and that negative came outside represented by I. Solving quadratic equations for imaginary roots. So every polynomial and every quadratic is going to have the number of roots that the degree is. So if it's a quadratic, that's to the second power, meaning there's going to be 2 roots. Now it could be 2 real roots, or it could be 2 imaginary roots. It can't be one of each. The quadratic formula could be used to solve for these, but I actually have a shortcut for you. So I want you to know that roots is really the same thing as x-intercepts, which is also known as zeros. But if you're ever talking about imaginary, you can't say imaginary x-intercepts, you want to call them imaginary roots. And so the shortcut that I have for you is a little formula. If you have a quadratic of the form, now you'll notice I changed this a little bit from standard form, x squared plus dx plus e, the imaginary roots are going to be of the form a plus and minus bi. They can be found using these 2 little formulas. And I changed the standard form from ax squared plus bx plus c because we have a and b in the standard form of a complex root. So I wanted to change this. This is just x squared plus dx plus e. So your a value of your root can be found using the formula 2a equals the opposite of d, and then the b part of your imaginary root can be found using a squared plus b squared equals e, found up here in your quadratic form of your polynomial. So let's do example 1. So I want you to find the imaginary roots, not using your calculator, not using the quadratic formula, just using the little shortcut. So 2a is the opposite of d. Well, the opposite of d right here is negative 2. So 2a is the opposite of d. That's going to mean that 2a equals 2. And so then a, the a part of my complex root is just going to be 1. The second part, I'm going to plug in the 1 squared. I don't know b yet, but my e is the 17 over here. So 1 squared plus b squared equals 17. I want to get b by itself. So that means if I subtract 1 from both sides, b squared equals 16. Take the square root, and b is going to be plus or minus 4. And so then the roots for this polynomial, you can either write it as 1 plus or minus 4i, or you can write it out separately to be 1 plus 4i and 1 minus 4i. Either one would work. Let's go to example 2 in the last one of our notes. It's 2x squared minus 8x plus 26. Now you'll notice there is a number in front of x squared. In order for the shortcut to work, you can't have a number out there. You need to factor that number out. So we're going to factor the 2 out. So then we get 2 times x squared minus 4x plus 13 equals 0. And so now I'm only going to use what's in parentheses. My d is now negative 4 and my e is 13. So 2a equals the opposite of d is the first part of that shortcut. So 2a is the opposite of negative 4, which is just a positive 4. And so then that means a equals 2. Plug that into the formula a squared plus b squared equals e. So then I get 2 squared plus b squared equals 13. And so then b squared, if I subtract 2 squared from both sides, I get 9. So then b is a plus or minus 3. And therefore my imaginary roots of this parabola are 2 plus and minus 3i. So this video covered section 2.1 on complex numbers, and you should be able to add, subtract, multiply, divide, and simplify complex numbers.